Good morning, doctor.
So we will continue chapter 16. First, I will go over formulas for banding, and then we start problems on it. So whenever we are talking about banding, we should know some important terms in sheet metal banding, as can be shown in the figure. So first, you can see here the metal thickness. So we have the metal thickness here, T. We have the width of the work part, W. We have the band radius, R, which is the inner radius. And we have the value of the included angle, alpha prime, while the band angle is the angle from the neutral axis plane at the initial state final to the final state. So you can see here, this is the alpha. So this is the band angle alpha. And the included angle is from the inner side alpha prime. And we can say that alpha plus alpha prime is equal to 180. Okay. In general, they give the band angle. So when they give the band angle, it is alpha. Okay. So in this case, as you can see, during the bending operation, you will have the outer part will tend to stretch, while the inner part will tend to reduce length, have reduction in length. And we have an axis that will have unchanged length, which is the neutral axis. Okay, so in order, if we know the final dimensions desired, we should take into account the stretching and compression of these parts during the bending operation. Okay, so in general, what we know, the final dimension, we consider the dimension of the neutral axis that should be desired. And during bending, we can determine what would be the inner length. Okay, so the at neutral axis we should have a higher length due to the bending due to the stretching effect. Okay, so the problem in any bending operation is to know how much we will have change in dimension between the inner length, the neutral axis length, and the outer length. This is why we will determine what is called the bending allowance. Okay, the bending allowance will permit to us to find what will be the difference between the inner length and the length at neutral axis. Okay, so here, if the band radius is small relative to the stock thickness, the metal will tend to stretch during bending. It is important to be able to estimate the amount of stretching that will take place in order to know what will be the dimension of the initially of the work part. So if any, so that the final part length will match the specified dimensions. The problem then is to determine the length of the neutral axis before bending to account for stretching of the final bend section. Of course, the neutral axis will not change in dimension during bending لأنه اسمه neutral axis, so it will have same length before and after the operation. But in general, they give us the dimensions if we know the radius of the inner side. Okay, and we know these dimensions. So this is what we know in general. We know these dimensions. So the neutral axis will be larger than the summation of these dimensions due to the fact that when we have bending, the neutral axis length will remain the same, while the inner part will be reduced in length, and the outer part will be increased in length. And since we know the inner part length after bending for the final part, then we can determine the value of the neutral axis length by taking the length after bending of this part plus what is called the bending allowance. And the bending allowance is calculated using the following relation. it's 2 pi times alpha over 360 times r plus this term. This term will take into account the stretching effect. So it is kBA times T. Okay, the value T is the thickness, and this coefficient will be given. So AB represents the band allowance. In case you are using SI units, if you use R in millimeter and T in millimeters, then you will get A in millimeter. Alpha represents the band angle in degrees. Here in this equation, it is in degrees because you already in the equation have the conversion to radian. Because when you do 2 pi over 360, you will convert from degrees to radian. And concerning the coefficient kBA, it depends on the relation between the radius and thickness. Okay, so in case we have the radius smaller than 2 times the thickness, the value of kB relative to A will be kBA will be 0.33. In case the radius is higher or equal to 2 times the thickness, then kBA will be 0.5. Okay. Now, another effect that is observed in bending is the spring back. So, what is the spring back? When the bending pressure is removed at the end of the deformation operation, one part of the elastic energy will remaining in the bend part will cause it to recover partially towards its original shape. This elastic recovery is called spring back, and it is defined as the increase in included angle of the bent part relative to the included angle of the forming tool after the tool is removed. And this is shown in the figure here. So look, you will force your part to deform in this way. So you will have a certain value of alpha prime. But when you remove the punch, then a part of the energy that is still in my work part, the elastic energy in it, will tend to recover a small part of energy. So you will go back, if you want, not to, of course, not to the initial state, but you will have a small recovery. So here you have, let's say, a certain angle, alpha prime. After the spring back, you will have a larger value for alpha prime. So you will tend to restore a little bit to go. Initially, this was your surface. It was a flat plate, okay? So it will tend to a little bit be closer to the initial state. So after removing, before removing the punch, this was your angle. When you remove the punch, it will try to recover some part of the energy. So this angle will be increased, okay? And in this way, we can, in general, when we do the design, we know that we will have this effect. This is why, let's say, if we desire a certain angle, if we desire an included angle, for example, here, if the final angle should be 30, for example, let's say, then in the operation we should choose a smaller angle because we know that after spring back we will have an increase of the included angle. Okay. So the spring back is calculated as alpha prime, which is the value of the included angle of the sheet metal part, and minus alpha prime t, which is the included angle of the bending tool, over alpha prime t. So of course, alpha prime is higher than alpha prime t. So although not as obvious, an increase in the bend radius also occurred due to elastic recovery. So you can see it in the figure. So when alpha prime increases, the bending radius also increases. Okay. And the amount of spring back increases with modulus elasticity and yield strength of the work metal. So each metal is characterized by its own spring back ratio because the spring back ratio will depend on the elasticity of the material and its yield strength. Now, what about the bending
دكتور
force that, yes?
بس فيك تقولي لي أين الألفا وألفا برايم تي على الفيجر؟
Yes, sure. Alpha prime T is this one of the tool. يعني أنت when you do the operation you will force your your work part to take the same angle of your punch. Okay, this is alpha prime t. Okay, now when you remove the punch, then your sheet, your work part will have an increase in its included angle. So the included angle will be little bit higher than the included angle that was imposed by the punch, by the tool. So this is alpha prime. Okay, so alpha prime will be the angle of the sheet after removing the tool. Okay, while alpha prime t is the angle of the tool which is imposed to your part when you do the operation. Okay, okay. Now concerning the applied force, okay, the applied force during a bending operation is estimated by the following equation. It's a certain coefficient times the tensile strength of the metal of the working part, the width of the working part times its thickness square over d, where d is the die opening dimension. Now, as you can see in this figure, you have two types of die operations. You can have V die or wiping die. Okay, so depending on the type of operation performed, the coefficient K will be different. So this formula is common for both, but with a difference of K between V die and wiping die. So in case it's a V die operation, a V bending operation, we take the coefficient to be 1.33, while for edge bending we take K equal to 0.36. Okay, so in case of edge bending, it's a wiping die. In case of V bending, it's a V die geometry. So this is the thing we should know about the bending process. Now we will do some problems together. In the following figure, a bending operation is to be performed on 5 mm thick rolled steel as shown in the figure. Determine the blank size required. Okay, so here, whenever they ask, the blank size is the initial state of your work part. So this is the initial sheet. The initial sheet is flat. Okay, and want to determine what should be its length in order to perform this bending operation. So as I told you, during bending, the only part which will have same length is the neutral axis. This is the neutral axis. The neutral axis will have the same length during the initial state and after bending. Okay. Now, why here? How we will find what is the length of the neutral axis? So the total length of the neutral axis in this figure is equal to the length of your blank part, which is the initial part. Okay. So we can say here that to determine this length, we should know the length of neutral axis. Okay. Now, to determine the length of neutral axis, we will use the formula of bending allowance, because the neutral axis will be equal to the inner length here inside plus the bending allowance. Okay. Now, how to calculate this length? We have this is 58, so plus 46.5, and we still have the part here. It's a circular part. We know the inner radius. Okay. Now, from this information, we should determine the bending allowance, which is depending on the radius and on the angle, on the bend angle alpha, to determine what is the value of bending allowance to add it to this length here. Okay. So let us see the details of calculations. So here we are repeating for you the formulas in the course to remember the formulas to be used. So first, remember always that alpha prime is the included angle inside. while the band angle is the remaining part. So this is the band angle. Okay. So if the included angle is 40, so in the figure here you have the included angle. You can deduce that alpha, which is the band angle, is 180 minus 40 equals to 140 degrees. Okay. So here alpha is 140. We know that the formula for bending allowance, the bending allowance will give you, if you want, the summation. Yani, this is the length of the inner part. The bending allowance will give you this length, which correspond to the length on the neutral axis, because the neutral axis will be equal to the length, if you want, imposed by the band plus the effect of stretching during bending, and you have this part is stretched and this part is compressed. This is why the neutral axis length will be higher than the length here. This is why you can determine the bending allowance as 2 pi times alpha over 360 times r plus this part. So this part is due to the effect of having the length of the neutral axis higher than the length of the arc of circle at the inner side. So we have that we have the value of alpha. The radius is given to be 8.5 millimeters. We still need to determine what is the value of k. To determine the value of k in this formula, we should compare the radius to thickness. So we do the r over thickness ratio. In case it is less than 2, we select the value of 0.333. In case it is higher than 2, we select the value of 0.5. Okay, so now all we have to do is to replace back into our formula. This will allow us to determine what will be the bending allowance. And now we are ready to calculate the total length of the neutral axis as 58 plus 24.8 plus 46.5. This will give us the value of the total length. Okay.
دكتور I have a question.
Yes.
إذا عطونا الأوتر راديوس نعمل ماينس الباند allowance ولا ما بتزبط؟
هنا على طول بيعطوك، ما هو انتبه على شغله، هنا على طول بيعطوا الانر راديوس. اوكي، ما بيعطوك الاوتر راديوس لانه already هيدي الفورمولا is developed based on الانر راديوس. اوكي، هلا in case عطوك الاوتر بدك تحط ماينس يعني of course. اوكي بس in general this formula is developed based on the inner radius. اوكي، لانه it might be ساعتها معقول يتغير ال coefficient، يعني it's an empirical relation at the end. Okay, since the empirical relation is developed based on the inner radius, then they should give you the inner radius. Okay, now any other question? Okay, another problem. Determine the bending force in problem 16.5 if the bend is performed in a V die with a die opening dimension of 40 millimeters. The steel has a tensile strength of 350 megapascal and a shear strength of 250 megapascal. So first, since it's a V bending, then we will select the value of, you know that the force is given by this formula as we have seen together. In order to determine the coefficient value, we should know if it's V bending or edge bending. Since it's a V bending type, we select K equal to 1.33. Now the tensile strength is provided, it's 350 megapascal. The width and the thickness and we can get them from the dimension of the plates here. So here our plate has a width of 35 millimeter and its thickness is given to be 5 millimeter. And concerning the value of D, D is given here. The die opening dimension is 40 millimeter. So all we have to do is to replace back into the formula and get the desired values. Okay. So it's a simple application on how to calculate the force. Another problem, solve the same problem except that the operation is performed using a wiping die with a die opening of 28 millimeters. So if the type of die is varying, the K will vary. Okay. So for an edge bending, we have the value of K equal to 0.33, and the die opening is 28. So W and T will remain the same, and the values of K and the D are changed. This is why we will replace by the corresponding values to get the force required to perform this operation with edge bending. Now we will introduce in order to do this problem, we will introduce the last part in this chapter, which is the drawing process. So we will learn what are the mechanics of drawing and how to determine if a drawing operation is feasible or not. So the drawing of a cup-shaped part is a basic drawing operation with dimensions and parameters as shown in the figure. So you can see here that initially you have, this is the initial part, okay? It's a flat plate, and you want to convert it into a cup, so it will have the geometry of a cup. So you will put first the initial part between the punch and die, and the punch will move downward, which will cause the formation of your work part to cause the formation of the desired shape, which is here a cup. Okay, so drawing of a cup-shaped part is the basic drawing operation with dimensions and parameters shown in the figure. A blank of diameter dB is drawn into a die cavity by means of a punch with diameter dp. The punch and die must have corner radius as shown, given by RP and RD. So the corner shape is to have a smoother operation. If the punch and die were to have sharp corners, RP and RD equals to 0, a hole punching operation, and not a very good one, would be accomplished rather than a drawing operation. So we should have a certain radius to have a smoother operation. The sides of the punch and die are separated by a clearance C, and this clearance in drawing is about 10% greater than the stock thickness. So in drawing, the clearance is different than the clearance we have seen in previous sessions. Okay, so in previous sessions, the clearance was calculated by AC times T, and we have a table to get AC depending on the metal type. Here, no, the clearance in drawing is function of the thickness. Okay, so we have, it is 10% larger than the stock thickness. So we can say that in drawing operation, the clearance can be estimated by 1.1 times the thickness of the blank part. Now, we have some conditions to have possible feasible drawing operation, and we will see them together. So it is important to assess the limitations of the amount of drawing that can be accomplished. This is often guided by simple measures that can be calculated for a given operation. In addition, drawing force and holding force are important process variables. Finally, the starting blank size must be determined. Okay. So as we said, this operation has some conditions to be feasible. So this is why we'll define some parameters, and we should satisfy the conditions of these parameters to have a feasible drawing operation. The first parameter we will define is the drawing ratio. So this is the most easily defined ratio for the case of a cylindrical shape, and it is the ratio of the blank diameter to the punch diameter. So the drawing ratio is dB over dP, and this ratio should not be greater than 2. Okay, so the greater this ratio is, the more severe is the operation, because if you have a very small punch and a very large blank, then you will have a very severe drawing operation. And it is not good to take a drawing ratio larger than 2. So the upper limit of drawing ratio is 2. The actual limiting value for a given operation will depend on the punch and die corner radius. Now the friction conditions and the depth of draw and characteristics of the sheet metal. So in general, these properties will also affect the limit, but as the maximum possible value of this limit is 2. Now, another way to characterize the drawing operation is the reduction ratio. So the reduction is calculated as diameter of the blank minus diameter of the punch over diameter of the blank. This ratio should be smaller, or this ratio should be, if you want, less than 0.5, and you can deduce this from the condition on drawing ratio, because the drawing ratio should be smaller than 2. Okay, and then if you replace here in this equation, dB over dB is 1 minus dP over dB, so minus the value of the inverse of the drawing ratio. Okay, since dP over dB should be, if you want, larger than 0.5. Why? Because you have that the drawing ratio is defined as dB over dP. Okay, so since dB over dP should be smaller or equal to 2, then the inverse, which is dP over dB, should be larger or equal to 0.5. Okay, and since here the ratio defines the reduction can be written as 1 minus dP over dB. Okay, since dP over dB should be larger or equal to 0.5, then 1 minus this ratio should be smaller or equal to 0.5. Okay, so if you want, these two conditions are equivalent, you can just check one of these two, because if the drawing ratio is smaller than 2, then the reduction, of course, will be higher than 0.5. Okay. Now, a third measure in deep drawing is the thickness to diameter ratio, T over dB. T is the thickness of the starting blank, and dB is the diameter of the blank. Often expressed as a percentage, it is desired that T over dB ratio be greater than 1%. So if you have very small thicknesses, you will not have a good final shape. Okay. So as T over dB decreases, we will have tendency for wrinkling, and this will not cause, it will cause a bad final shape. So in cases where these limits on drawing ratio, reduction, and T over dB are exceeded by the design of the drawn part, the blank must be drawn in 2 or more steps, sometimes with annealing between the steps. Okay, so this is why before doing the operation, we should verify that these conditions are satisfied. Okay, then we say that the drawing operation is feasible. Now, to see if the final product, if we can have at the end the final product desired, we should also verify a second thing that we will see together in the problem, which will depend on the final geometry desired. We will check it together in an application. So let us do a problem together. So first, a cylindrical cup is produced in a deep drawing operation. The cup height, so these are the final desired dimensions. The cup height is 75 millimeters, and its inside diameter is 100 millimeter, and the sheet metal thickness is 2 millimeter. First, if the blank diameter is 225 millimeter, determine the drawing ratio, the reduction, and the thickness to diameter ratio. Then conclude if the operation is feasible or not. So first, we have everything. All we have to do is to calculate our parameters. So the drawing ratio is dB over dP. Both are given. We get a value higher than 2. So here you can directly stop because you can say it's not feasible. But since they asked you to calculate the remaining ratio parameters, we will calculate them. But already since this ratio is not satisfied, then it's not, the operation is not feasible. Okay. So if the question was only is the operation feasible, you can stop from the first step. Now, for the reduction ratio, we will expect that it will be higher than 50%, because if the drawing ratio is larger than 2, then the reduction will be larger than 50%. And for T over dB, the thickness also is not suitable because it's smaller than 1%. Okay, so here all parameters are not good, and of course it's not feasible because dr is too large and also td is too small. So here, if one of the two is not satisfied, then the operation is not feasible. Okay, now what we will do now, we will suggest another starting blank size. Okay, so to see if with a blank size of 175, if it's possible to perform the operation. So first, by decreasing the blank size, then the drawing ratio was decreased lower than 2. The reduction, of course, will be then smaller than 50. And for T over dB, also the third condition is satisfied. T over dB is higher than 1%. But now we should pay attention. Okay, so we have another criteria to make sure of, which is if this blank size diameter will give me the final dimensions desired. So as feasibility, okay, the drawing operation is possible, but it will give me the desired geometry at the end. To make sure of this, I should determine if this blank size diameter is able of giving me the final geometry I need. So here, if you go back to your problem, what was the condition? You should have a cup height of 75 millimeter. You should have an inside diameter of 100 millimeter and a sheet thickness of 2 millimeters. Okay. Now, for the operation concerning the diameter, it is imposed by the punch. So the drawing operation can result in variation of height. So depending on the blank size, you will have variable possible heights. Okay. Now we should make sure that the blank that is used can result in a height higher or equal to 75. Because if it's higher, we can do a cutting operation to get a cup height of 75. But if it is lower than 75 millimeters, the final product height, we cannot do anything. Okay. So now we should verify that the blank diameter provided is suitable. So to do this, what we will do, we will say that the area of the blank, okay, should be minimum equal to the area of corresponding to 75 millimeter of height. So what we will do here together, we will verify what is the possible height to reach with a blank area of pi d square over 4. So the initial state of your work part is just, it is in the form of a disk. So the area of it, okay, can be calculated by pi d square over 4. Okay, so this is the initial geometry. It is in the form of a disk, and the area is calculated by pi d square over 4. Okay, now we have the diameter is given of the blank. It's 175 millimeter. Replacing back, we can get what is the initial blank area. Now, when you do the drawing operation, this area, we will have change in geometry. This area will be divided into the base area of your cup and your lateral area. Okay, and the lateral area. So how to compute this? Okay, this total area of your cup will be equal to the base area plus the lateral area, and assuming we don't have no earring of the cup. So the cup area, the base is given by pi d square over 4, pi dp square over 4, because the diameter of the cup is imposed by the punch. So here we replace by d punch. We get in this way the base area. Okay. Now concerning the lateral area, so to calculate the lateral area, it is this area here. This area is function of the final height. Okay. So it's equal to h times the perimeter of the base. So it's h times pi dp. Okay. So pi dp times h will give me the lateral area of my cup. Okay. So now I should compare the two areas. And here I will get area function of h. So this is a variable. H will depend on the blank area. So now I will set the two surfaces equal to each other. So the surface area of the cup should be equal to the surface area of the starting blank. Then, as you can see, I can get the value of h. And the value of h obtained that is possible from this blank area is 51.56 millimeter, which is smaller than the required height, which is 75. So this blank area, this blank size is not enough for me. Okay. So here, what I can do is I should try to find another combination of dp and db in order to have all criteria satisfied. Okay. So I will try to increase the value of dp while maintaining the three parameters satisfied. And I will look at a certain blank size that can give me this the height of 75, and that will satisfy for me the three conditions. So I can try to find what is